Bolzano Weierstrass Theorem. To start this theorem, let's revise one result which we have done in the earlier video. If Pn be a sequence in a compact metric space X, then some subsequence of Pn converges to a point of X. Remember that your space should be compact. If in a compact metric space we are having a sequence Pn, then its some subsequence converges to the point of the same space. Right? So we will use this result for proving this theorem. Now what this theorem states, Bolzano Weierstrass theorem, every bounded sequence in Rk contains a convergent subsequence. What is Rk? It is the kth dimensional space, right? So we are given a bounded sequence in Rk, and this sequence will contain a convergent subsequence. When we are having a convergent subsequence, just again revise the result. If we are having a sequence Pn in a compact metric space, then we can get a subsequence which converges, right? So let's see the proof. Let Pn be a bounded sequence in Rk. Then Pn is contained in some bounded and closed subset X in Rk, right? If it is a bounded sequence, then it must be contained in some closed and bounded subset of Rk. Let's say that subset be X. Now, what is the result? One more result is there. Every closed and bounded subset in Rk is compact. Just remember this result. I have proved this result in my first part, Real Analysis Course Part 1. So every closed and bounded subset in Rk is compact. So this closed subset which we have taken as my X, then this closed subset will be compact because it is closed and bounded in this Rk space. So in Rk only, the closed and bounded, every closed and bounded subset in Rk is compact. So my X is compact now, right? So since X is closed and bounded in Rk, X is compact in Rk. Now next, just we have got a compact space now, right? And in a compact space, we are having a sequence Pn, right? Just we need to prove that there is a convergent subsequence in it. And the same proof which we have done in the previous theorem, the same proof is there now. So I just revised the proof and explain to you again. What we have done in that proof, we have just guessed a range E. We have taken a set E to be the range of the sequence Pn. Then E is subset of X, right? Because the sequence itself is contained in X, and if E is the range of the sequence, then E is also the subset of X. Now two cases arises. Either E is finite or E is infinite. When E is finite, you know what we have taken the sequence for, just for an example? We have taken the sequence to be, let's say just for an example, let's say our sequence Pn is -1 the power n. That is -1, 1, -1, 1, so on. Right? Where your n belongs to the natural number. Now what will be the range for this sequence? The range will be the distinct elements. That is -1 and 1. Alright. Can we make a subsequence from this sequence? We can make a subsequence. We collect the points, either the points 1, 1, 1, that is Pn1, Pn4, Pn6, so on. Or either we take the negative ones, and all these points are same, right? So then there exists a point P belonging to E, whether that point can be -1 or 1. So there existing a point P in this E, and a strictly increasing sequence Nk, where Nk belongs to your natural number such that Pn1 equal to Pn2. See, this nk is a subscript for the subsequence. And if nk is belonging to natural number, that means your if this is your P1 in Pn sequence, this element is, second element is P2, third element is P3, then what are actually this nk for the subsequence? These are actually the natural numbers 1, 2, 3. So if you take your subsequence to be as for the point 1, then your subsequence will be the second element. You should look that element as Pn1, right? Then second element Pn4, so on. So this subscripts nk, that is n2, n4. This n2 is nothing but the number 2. This n4 is nothing but the number this 4, right? These are just representing the number. The subscript of P and K, these subscripts just represent the number, this 2, 4 for the sequence Pn, right? So my Pn1, Pn2, Pn3, so on will be equal to P, right? So most of the elements, most of what? All the 1, 1, 1, 1, 1 elements are equal. So Pn1, Pn2, Pn3 all are equal to the number P, right? Thus, the subsequence Pnk of Pn so obtained evidently converges to P belonging to E. Evidently it is converging to P belonging to E. And as all the terms are equal to the same number P, that means the subsequence is converging to the same P, right? And E is subset of X, and X is further the subset of Rk. Then what the P belonging to E will finally P is belonging to this Rk space, right? So we got a subsequence which is converging in Rk. Now thus Pn contains a convergent sequence in Rk. Now the second case, if E is infinite, then E has a limit point P in X, because E is an infinite subset of compact set X, so it must be having a limit point. Let's say that limit point be P. Let epsilon be positive given, since P is a limit point of E. That means, now the definition, every neighborhood of P contains infinitely many points of E. If the if the set is infinite, and if the infinite set is having a point P as your limit point, then the definition will be every neighborhood of that point contains infinitely many points of E, right? Now, thus, can I guess a neighborhood for P as NP epsilon? So this NP epsilon contains infinitely many points of E. Just say Pn1, Pn2, Pn3, right? So these are infinitely many. So here again we have to write Nk is a strictly increasing sequence so that order will not change, and the remaining elements for the Pn sequence will remain as there. Thus Pnk is a subsequence of Pn in E such that because all these elements of the subsequence, these are infinitely many which are contained in the neighborhood of P. So Pnk is the element of Np epsilon. And whenever the point is contained in some neighborhood, their distance with the P will be less than the radius for k greater than or equal to 1, because we have taken Pn1. We start our k from 1. But epsilon was arbitrary, so P and K will converging to P. This is your definition for the convergence. When the distance will be less than epsilon for any natural number, then that sequence, that elements of the sequence will converging to a point what we have taken. Now since P is element of X, the compact space, and further it is contained in Rk, then Pn contains a convergent subsequence in Rk. This P is now belonging to this Rk. So we got a convergent subsequence in Rk, right? Hence proof ends. All right. Let's do one more theorem. The subsequential limits of a sequence Pn in a matrix space X form a closed subset of X. Yes. What is subsequential limit? Suppose we are having a sequence Pn, alright, and its subsequence is converging to a point, say P, then that P will be the subsequential limit of the sequence Pn. Okay, right. Now that forms a closed subset of X. Now we collect all the subsequential limits of Pn. We make a set of that, right? And we have to prove that that set is closed subset of X. Now when the set will be closed? When the set will be closed? If all the limit points of the set belong to it, right? Then we say that set is closed if all of its limit point belongs to it. So let's start with the proof. We make a set of subsequential limits of sequence Pn. So let, I'm supposing E star to be the set of all subsequential limits of Pn, and let's say let's guess the limit point for that. Let Q be the limit point of E star. Okay, let's say Q be the limit point of E star. Why I have taken this limit point? Because I need to prove that this E star is a closed subset. And to prove that this set is closed, I need to prove its limit point belong to it. So that's why I have taken Q to be the limit point of E star. Alright? So just I have to prove that this Q belongs to this E star. Then only this E star is closed. We have to prove this now, right? Okay, let epsilon be positive given. Right? Since Q is the limit point of E star, therefore there exists a neighborhood of Q. I'm taking the radius to be epsilon by 2. Right? Therefore, this neighborhood of Q contains, now the definition for the limit point, one more definition, that every neighborhood of this Q point contains a point, at least one point of E star other than this Q. It contains at least one point of E star other than this Q. So it contains at least one point of E star other than Q. Fine? Alright. Thus, suppose we take one more point from E star instead of Q. It contains at least one point of E star. Let's say that one point in E star will be your X. 1 point X. Suppose X is another point from E star. So X is containing in this neighborhood. If X is contained in this neighborhood, that means its distance from Q is less than epsilon by 2. So the distance for this point Q, for this point X with Q, is less than epsilon by 2. Right? Now, we are saying this other point X to be in E star. That means what is X? X is the subsequential limit of Pn. Since X is the element of E star, that means X is the, if it is the element of E star, X is the subsequential limit of Pn, sequence Pn. Fine? Okay. Now we are having a subsequential limit for Pn. Just writing the definition for the subsequential limit now. That means there must exist a subsequence of Pn which is converging to this subsequential limit x, right? As x is a subsequential limit of the sequence Pn, thus there exists a subsequence Pnk of Pn which converges to x. Right? So can I write it as, since Pnk is converging to x, right? So therefore, just the definition for the convergent sequence now. There exists a positive integer n such that since it is converging to x, let's write the definition for the convergence in the distance format. So the distance of P and k with x is less than epsilon by 2 for, I'm taking now, instead of epsilon, I'm taking epsilon by 2 because this number can be as small as possible you can take, but positive 1 for k greater than equal to n. This k is greater than equal to this natural number. Alright. Now, what we need to prove? We need to prove that the q, the limit point, should belong to the E star. Right? This we have to prove. So, I am guessing, taking the distance of P and k with q. See, this x is the subsequential limit, right? Because x is contained in E star, we say that x is a subsequential limit. If I prove, now what I have to prove? Q is contained in E star. For that I need to prove Q is also the subsequential limit of E star. Is it clear? See, we have taken x to be the subsequential limit of E star. And we say that this x belongs to E star as, so this is a subsequential limit of E star. What we need to prove? We need to prove E is closed. For that we need to prove its limit point belongs to E star. We have taken Q to be the limit point of E star. Right. When this Q will belong to E star? If Q is the subsequential limit of E star. So that's why I'm taking the distance of P and K with Q. If this distance will be less than epsilon, we say that this P and K will, if this distance is less than epsilon, we say that P and K will converge to Q. And whenever the subsequence is converging to a point, that point will be the subsequential limit of Pn sequence, right? And then automatically this point will belongs to the E star because it will be now it is now the subsequential limit of the Pn. So just I need to prove that this distance is less than epsilon. Just this I have to prove now. Alright. So what this distance is? This is less than equal to the distance of P and K with x plus the distance of x with q. This is your identity, right? Now what distance P and K with x is? This is less than epsilon by 2, right? And what this distance is? Distance of x with q. This is less than epsilon by 2, say. This distance is, okay, sorry. This distance is less than epsilon by 2. And this distance P and Kx, this is less than epsilon by 2. So we have taken both the distances. Say it as 1. Say this as 2. From 1 and 2 we write these two distances less than epsilon by 2, and this is nothing but epsilon. Proved. So what we have proved, that is distance of P and K with Q is less than epsilon, right? For K greater than equal to N. But epsilon was arbitrary. What we got? Whenever this distance is less than epsilon, that means your P and K is converging to Q now. That means, therefore, P and K is converging to Q. But P and K is a subsequence of Pn. And whenever subsequence is converging to a point, this point will be the subsequential limit of Pn. And what we have taken E star to be the subsequential limits of Pn. That means, thus, this Q is now belonging to E star, because E star is the set of all the subsequential limits of Pn. But Q was arbitrary. Q was arbitrary. That means every limit point. What is Q? We have taken Q to be the limit point of E star. That means, as Q is arbitrary, that means not for one point, for every limit point. Every limit point of E star belongs to E star. Right? Thus, and whenever this thing happens, we say that E star is closed. This is what we have to prove. Thank you.